Okay, well, we're going to dive right into ultrasound physics and instrumentation. And while this may not be the most exciting topic to start off with, I assure you it is foundational to apply ultrasound clinically. And even though physics is in the title of the presentation, do not let that frighten you. In classic MedCram style, we will break down the concepts so that they are easy for you to understand. In this course, we are going to define ultrasound. We will discuss basic ultrasound physics. We'll touch on ultrasound biosafety and the ALARA principle. We will discover different ultrasound transducers and their applications. We will look at ultrasound orientation and common ultrasound terminology. We will explore ultrasound knobology, or the different knobs and controls that you need to know on the ultrasound machine. We will look at the ultrasound modes, we'll discuss ultrasound artifacts, and we'll finish up with a step-by-step guide on how to perform an exam on a patient. Well, let's start off by defining ultrasound. And if this line represents all of the possible audio frequencies that exist, then a portion of those frequencies are audible, or those that can be heard by the human ear. And this is said to be 20 hertz to 20,000 hertz. Well, then everything below the hearing threshold is said to be infrasound or subsonic. Then everything above the hearing threshold is said to be ultrasound. So ultrasound is simply sound waves that are above the hearing threshold. In diagnostic medical ultrasound, the frequency ranges typically are 1 to 20 plus megahertz that are being used. Before we dive into ultrasound physics, I want to briefly explain how an ultrasound machine works. And while you may not be familiar with an ultrasound machine, you're likely familiar with the speaker. And since they both generate sound waves, it provides a good example. The speaker uses electrical energy, and the electrical waves that travel through the speaker cable cause the speaker to pump in and out. This generates sound waves in the air, which are then heard by the human ear. Well, similarly, the ultrasound machine uses electrical energy. The electrical waves generated by the ultrasound machine travel down the transducer cable into the transducer, and the transducer produces sound waves. But in this case, some of these sound waves reflect off of the patient's tissues and are transmitted back to the transducer. The transducer then, at this point, converts the sound waves that it's receiving back into electrical energy, which is then processed to form a visual image on the ultrasound machine. So let's look at this another way. You have your ultrasound transducer and your patient. The ultrasound transducer generates a sound wave. It's transmitted through the patient's tissues, reflected back to the transducer, and then those returning sound waves, or those returning echoes, are processed to form a single scan line. Now, there's a few components of the scan line that I'd like to discuss, and one is depth. Depth is a function of distance to the ultrasound machine, meaning the longer that it takes to return to the ultrasound machine means it had to penetrate deeper into the tissues. And the ultrasound machine knows to place those returning echoes deep in the scan line. Conversely, the more shallow that the ultrasound wave must penetrate and reflect back, the less time it takes to return, and therefore the ultrasound machine knows to place that more shallow on the scan line. The second component that you'll notice is the brightness. And think of the brightness as the volume of the returning echo, if you will, or the intensity of the returning echo. The louder the returning echo, the brighter it will appear. The quieter the returning echo, the less bright it will appear. So a more intense returning echo will appear brighter, and a less intense returning echo will appear darker. Well, this same process happens again to form another scan line. And this repeats in a sequential fashion to form a 2D image. Now, in this 2D image, you can pick out the individual scan lines. And that's because it's an old ultrasound image of a fetal skull. But in modern ultrasound images, you will no longer be able to see the individual scan lines. It will appear as a homogeneous 2D image. But the image is still generated in the same fashion. So now that we understand how an ultrasound machine works, let's return to our discussion of ultrasound physics. As we touched on before, as the speaker pumps in and out, it generates sound waves. Well, how does it really do this? Well, as it pumps out, it compresses air molecules. And these areas of highly compressed air molecules are called compressions. And as it goes back in, it creates this vacuum effect. And there's areas of low pressure called rarefactions. And with this alternating in-out movement, it creates alternating compressions and rarefactions. And for this course, we will illustrate compressions as a sound wave, like this, and the space in between them as rarefactions. So for us to discuss the characteristics of a sound wave, it's much easier to depict the compressions as peaks on a sine wave and the rarefactions as troughs on a sine wave, although we understand that a sound wave is not a sine wave. But the first characteristic of a sound wave we want to discuss is the wavelength. And the wavelength is the distance between a peak and a trough and a trough. And similarly, the time between a peak and a trough is called a period. So wavelength is a function of distance, and period is a function of time. The next characteristics we'll see is the amplitude. And amplitude is the height of the peak of a sound wave, or how high pressure the compression is. This is the loudness or the intensity of the sound. So the higher the amplitude, the louder the sound, or the more intense the sound. The lower the amplitude, the less intense the sound is. And then lastly, we'll look at frequency. And frequency is how many sound waves travel past a certain point in a certain period of time. And frequency is measured in hertz. And hertz are cycles per second. So the more waves that pass a given point in a second, the higher the frequency. The less sound waves that pass a given point in a second, the lower the frequency. Okay, well, to make sure we understand these characteristics of sound waves, I want to do a few examples. So we're going to compare these various sound waves. And if we compare the top wave to the middle wave, we'll notice the wavelength of the top wave is longer compared with the wavelength of the middle wave. Therefore, since the wavelength is longer, the frequency is going to be lower. And therefore, the pitch of this sound wave on top will be lower than the middle wave. If we look at the amplitude of the top wave compared to the middle wave, however, is lower. Therefore, the volume or the amplitude of the top wave will be quieter than the volume or amplitude of the middle sound wave. And the bottom wave has an even longer wavelength, therefore a lower frequency, and it also has a lower amplitude than both the above waves. So therefore it will be lower and quieter. And if you look at this, you'll notice a key concept that frequency is inversely proportional to wavelength. Meaning, the bigger the wavelength, the lower the frequency. And the smaller the wavelength, the higher the frequency. So what does this have to do with diagnostic medical ultrasound? Well, it primarily boils down to these concepts of resolution versus penetration. Now, resolution simply is how pretty your picture is, how defined and detailed the ultrasound image is. Penetration simply is how deep the ultrasound wave is able to penetrate into the patient's body and therefore generate an image. And these things are primarily a function of frequency. See, as you increase the frequency, you improve the resolution. And as you decrease the frequency, you decrease the resolution, or the resolution gets poorer. Now, the converse is true of penetration. As you increase the frequency, you decrease your ability to penetrate into the tissue. And the opposite is true. Where you decrease your frequency, you actually increase your ability to penetrate into the tissue. Now, if this doesn't make sense or seem too abstract, let me give you two illustrations. One is in photography. In the age of smartphones all having cameras, many people know that the camera's resolution is rated in megapixels. So the higher the megapixel on your camera, the better the resolution is, or the prettier the picture will be. But as you know, if the object you are trying to take a picture of is a far distance away, your resolution decreases. You've all zoomed in on your smartphone when the object is far away and the picture gets all grainy and you can't see it as well. It's because the better the resolution is when the object is closer to you. Or another illustration would be in music. You've all driven by a stadium concert, and when you're half a mile away from that concert, you can actually hear the bass. You don't hear any of the rest of the music, you just hear those very low frequencies. It's because those low frequencies, those large wavelengths, can travel a long distance. They can penetrate very well, but they're not well defined. You can't hear the detail of the low frequency. Where if you were to go into that stadium and put your ear right up against the speaker, it would be the high frequencies that pierce your ear because they're very well defined, but they cannot travel a far distance. All right, well, that wraps up how an ultrasound machine works and the basics of ultrasound physics. Next, we will look at the interactions of ultrasound in tissue.